In this video, I have to be so extra. In this video, we are going to work on the Euclidean geometry grade 12 proportionality theorem, specifically the proof. So if this is something that has been giving you a hard time, well, you are in the right place because this is what we're working on. Hi guys, Levi here from Bright Young Brains. Okay, so to just try and lighten things up, this theorem or this proof or this work in general is something that freaks a lot of people out, and I'm not excluding myself, because this is not very comfortable. However, it may be uncomfortable, but it does not mean that we should always be okay with not knowing the basics, or we should always be okay with not understanding how it works. So simply put, right, with our proportionality theorem, before we prove it, all we want to take note of is that, for example, with our sketch, right, we have two main pictures to focus on here. When I say two main pictures, I am referring to the triangle at the top here, ADE, and the big one down here. Well, not down here, but the big one. So with these two triangles, the big idea is, because this line is parallel to this line, automatically those two angles are corresponding, and those two angles are corresponding. So what that means is those two are equal for the two triangles if you look at them separately, and those two are equal. Automatically A there will be equal to A there because this is a common angle, you see. So by default, our two triangles are similar to each other. Now, whenever you have similar triangles, this is the big issue. Try and look at the different sides in an order that is the same. This is what I mean. We could literally write out our own ratios or whatever, as long as we make sure that what we do for this triangle, we somewhat do the same for the other one. Let me give a basic example. Here, if we, let's say, have lengths in this one and we have some lengths in this one, and we want to link the two, as long as these two triangles are similar, you just want to focus more on the angles that match. You see, this matches with that, this matches with that, this matches with that. So that being said, I can write out a ratio here. For example, I can say here AE over DE. That, right, is automatically going to be equal to AC over BC. You see, the reason for that is whatever I did here, I mimicked the same thing on the other triangle. You see, we just went AE over DE is equal to AC over BC. That may be something you already know. Yay. I mean that in a good way. Fantastic. So just another random example. We could say stuff like AD over, let's use this other triangle. You see, AD, if we're going to use AD for this picture, for this one we can use AB. You see, AD over AB is equal to any other side here. Let's choose AE over AC, right? Because as long as our motion is the same, we can write out whatever we want. What I mean is, you see here we used AD, and then for this one we used AB. You see, this goes with that. You see, they are corresponding. And then for the other portion we used AE and AC, you see, because those go together. Now, that being said, this is the basics of working with similar triangles. The only idea is when you're looking at them in like a sketch that is meshed up, you see, you have a big triangle here, and then they have automatically thrown ADE inside it because these two are parallel. You see, when that is done, always try and remember that you basically have two triangles, the small one here and the big one. Now, when you now have your triangles in this order, your ratios, or what you can write, you somewhat have more of that. What I mean is, here we can easily say stuff like AD over DB, right? That's going to be equal to AE over EC. You see, can you see? Because the motion is the same. I did this here and I did that there. So on the other side, I can do the exact same thing. That and that. The reason we can write out stuff like that is because of our proportionality theorem. The sketch in itself has two triangles, and then because of the way those two triangles are like similar to each other, these are stuff we can write out. We know that later on we're going to prove this. However, we need to really get to understand that all we want to remember is as long as what we do matches and goes together, we can write whatever we want. I'll just give us another blunt example. If we had or have the same sketch, you see, we have the same sketch, we know that these two are parallel, we could easily write out stuff like, let me put here DE over BC. This can be equal to, so what you want to take note of is, can you see I used this line for the small triangle and I used the corresponding line for the big triangle. So all I can do is for the small one, I can also just pick, let's for example go with AE over AC. You see, what we have written down is valid because you see we have taken the small triangle, the big one. You see lines that are corresponding, as in lines that go together. You see that we said it is equal to AE, which is for the small triangle, over AC, which is for the big triangle. You see, so I keep saying you see, I hope you do see. So at the end of the day, the one thing you want to focus on is writing out your ratios based on triangles that you're focusing on. Don't just think you have random lines that you need to just throw random arrows for or something like that. Not necessarily. That's not what's happening. You are not drawing random lines. You just want to draw things that go together based on the triangles that you are focusing on. You see, I'll just do one other random example to try and explain what we have just said here. Okay, so we have our sketch here again. Now, what I could also write out is, let's try and switch things up a bit. Let's try and make things a bit difficult, I guess. So let's say here we could easily, let's choose AD over AE. We see small triangle, small triangle. I think this one is going to be easy. But then let me try and put a twist in it. You see, AD over AE is easily equal to, well, in this case, it would have to be AB for the big one, right? Over AC. There we go. So I was trying to make this a bit difficult, but you see, it's even hard to make it difficult because as long as you see that, oh, we're just working with the triangles and how they are related, then it makes things easier. You see, because when you're able to look at them separately, you can see how you can easily write this out. But then when they are all meshed up, you can still easily write stuff like this out as long as you focus on those two triangles. You see, because all we've done here is we have technically said AD, right, over AE is equal to AB for the big one over AC for the big one. You see, I mean, I think it's pretty much clear now. Yeah. As long as this is clear, we now are comfortable with working with this theorem. Proving it is going to be something you just need to be able to regurgitate onto the paper. You just need to learn the basics of the proof, which we're going to cover now, and then you just need to know the steps. You don't want to cram what we're about to show now. You want to remember the key steps, and I am going to make sure that I properly lay out those key steps so that you're always able to remember them in an exam when you need to prove this theorem here. Because basically what they're trying to have us prove is that AD, if you check the AD over DB, you see, AD over DB, we should prove that it is equal to AE over EC. So in our proof, we're going to work on how all this is linked. So now for our proof. If we are going to prove that AD over DB is equal to AE over EC, this is what you need to do.